Hello everyone. Welcome to an introduction on evolutionary algorithms. Before I go on to introduce myself, I want to make it clear that I don't expect you to have any pre-existing knowledge of the subject or any scientific background. This introduction is intended for everyone, especially those who are interested in learning about something new. Because of this, I'm going to try to explain everything in plain English. So who am I? My name is Shahin, and I'm a lecturer at the Bournemouth University, which is on the south coast of England. My PhD thesis from years ago, as well as my current research interests, include evolutionary computation. So for me, this is something I find very interesting and a topic I enjoy talking about. This is also my first public-facing video, so please bear with me whilst I adjust to the format. Here is the presentation overview. I want to get you excited about evolutionary computation before I tell you what it is. Hopefully, this will give you an incentive to engage with the rest of the video and convince you that it's not a waste of time. Then, I'll very briefly tell you what it is, before moving on to a high-level example of how it works. This includes a quick activity, so if you want to take part, please have a pen and paper ready. We will then conclude with some recommendations for further reading and tinkering. So, why should we care about evolutionary computation? One of the reasons I give when I'm trying to get people interested in the subject is the variety of potential applications. Here you can see a short list of just a few areas where I've applied evolutionary computation. Starting with the more serious and higher impact applications, and moving on to what I feel are the more fun applications. Because of evolutionary computation, I've had the opportunity to not only work on these kinds of projects, but also work with brilliant people from the associated fields. For me, this is one of the most rewarding parts of working with evolutionary computation. Towards the end of my PhD, I had the opportunity to apply evolutionary computation to a concealed weapon detection system. This type of application concerns the safety of others, and any improvements made can positively impact this safety. It can also be applied to designing AI behavior for video games, where, for example, we can focus on creating a Mario who is greedy and wants to collect as many coins as possible. There are many applications for evolutionary computation, and we've barely scratched the surface in these last few minutes. Finally, let's talk about what evolutionary computation actually is. It's a nature-inspired approach to optimization, which is the process of getting the most out of something and making it better. During this process, we are in the search for the best or optimal solution to a problem. It's inspired by this idea of survival of the fittest from Darwinian evolution and Mendel's modern genetics. The general idea behind the whole thing is that if biological evolution can produce something as amazing as humans over many generations, then we should be able to use the same process artificially to evolve optimal solutions for vehicles, aircraft, spaceships, and so much more. To dispel any overhyping, it's worth noting that in practice, evolutionary computation offers approximations of optimal solutions to difficult problems. Often, it can be overhyped as the all-powerful hammer where every problem in existence is a nail. This isn't the case. Now, on to the fun stuff. How does an evolutionary algorithm actually work? Here you can see a flow diagram of a simple evolutionary algorithm. You can see different stages which flow down to the bottom and then loop up back near the top. Let's go through each step one by one whilst working through an example. The first stage of any evolutionary algorithm is initialization. We can think about this stage as some kind of Big Bang, where we create our initial population out of nowhere. We call a group of solutions to a problem at any stage of the progress a population. and in this case we have randomly generated our solutions. It's important to define our data structure, often referred to as a chromosome in the context of evolutionary algorithms. This chromosome simply stores a set of items, or genes, which describe our solutions. We can think of this as some type of blueprint. Here we have a population of 6 solutions, which I have labelled A through to F. Each solution is defined by its own chromosome, and here you can see that each chromosome stores 6 different genes. These describe the lengths of the arms, legs, torso, and the size of the head for each solution. With our initial population generated, we move on to the evaluation stage. This is where we figure out the fitness of each of our solutions. The fitness is often a single number which gauges how good a solution is. The higher the number, the better the solution. We need this information later on if we're going to apply this idea of survival of the fittest. Of course, this fitness value depends entirely on the problem we are trying to solve. In this case, I have made up a simple problem for the purpose of this demonstration. Below, you can see a track with a hurdle in the middle. For this problem, we are trying to find the stick figure which is best suited for completing the track, which involves getting over a hurdle. We'll use the numbers below the track as the fitness value, because it indicates how far each stick figure made it. So, we need to evaluate each solution. This means making them run the track, one by one. Solution A is up first. It's worth noting at this point that I have no experience with animation, so these stick figures will simply begin at the starting line and appear at the furthest they can make it. It also appears that solution E has lost its confidence. Here we can see that solution A only made it up to the hurdle, because it doesn't have long enough legs to make the jump. Solution A received a fitness score of 250, which it seems happy with. Now it's solution B's turn. It appears that solution B has made it past the hurdle and achieved a fitness score of 350. Now for solution C. It appears that solution C's wide head has prevented it from getting closer to the hurdle, so it settles for a fitness score of 240. Solution D's turn. And he scores a painful looking fitness score of 320. Now for solution E's attempt. It rolls a respectable fitness score of 10. As we can see with solution F, not every solution is built to perform well on the problem. This is due to the random nature of the evolutionary process. Unsurprisingly, its fitness score is 0. And now we have a fitness score for every solution in our population. Now that we are in what is called the generational loop, where we will try to improve our solutions over and over again, we need to figure out when to stop looping so that the process doesn't continue forever. This is called the termination stage. At this point, we would check the current state of the evolutionary process to see if we've satisfied some of the rules for stopping. These rules would be defined before starting the evolutionary process. Here, I've given an example of some of these rules, which we will refer to as termination criteria. The first one is whether the goal has been achieved. So maybe we have an ideal fitness score in mind, and we'll check our solutions at every generation to see if any of them have made it. If so, we'll stop. Otherwise, we'll continue. Maybe we just want to run the evolutionary process for a specific number of generations. So, we'll check to see if the current number of generations has reached the maximum allowed. Or, we simply terminate the process when there is no longer any significant improvement being made to the fitness scores from generation to generation. For the purpose of this demonstration, Let's assume the termination criteria has not been satisfied, so we can continue to the next stage. This stage is called selection, and this is where survival of the fittest takes place. If we were to pick 3 solutions from this population to produce offspring for future generations, which 3 would we pick? Typically, we would select the 3 solutions with the highest fitness score, because we expect these 3 to contain the most valuable genetic information, and we want this genetic information to be passed on to the new solutions. Now it's time for the variation stage. Here we will aim to use our selected solutions, which we can refer to as the parent population, to produce new solutions, which we can refer to as the offspring population. One method of variation is called chromosome crossover. Here you can see the same chromosome from before, but this time I've placed a red line in the middle, indicating 2 different halves, which I have color-coded with blue and green. We'll now use this red line, or the crossover point, to mix 2 parent solutions to produce a single offspring solution. Let's use the following scheme. We're going to pick the parent with the highest fitness score. From it, we will take the blue part of the chromosome. We'll then pick the solution with the highest fitness score from the 2 remaining parents, and from it we will take the green part of the chromosome. We'll stick these 2 halves together to form our new offspring solution. And then start the process again, but this time with the parent with the next highest fitness score. Let's see what happens. Here we can see parent B and parent C have produced offspring D. I've color-coded the parts of the stick figures to indicate what has been passed on to the offspring and which parent it's come from. Next, we can see parent C and parent B have produced offspring E. You may notice the same parents have been selected for the crossover, but in a different order, which has changed which parts have been passed on to the offspring. Now for the last offspring. We can see parent B and parent A have been selected for the crossover. And now it's time for the quick activity. If you want to take part, please just use a pen and paper to sketch out what you think offspring solution F will look like. Your 15 seconds start now. And there we have it. I hope your offspring F looked similar. If not, you can see with the color coding how we arrived at the answer. Now we're done with crossover. However, if the only method of variation we ever use is crossover, then we'll never introduce any new genetic information into our population. This is because at every generation we will just be mixing together the same genetic information which we started with at the initial population. To solve this, we use another method of variation which is typically used together with crossover. This is called mutation. With mutation, all we do is select a random gene on the chromosome of a randomly selected solution. Then we add a random number to this gene. This introduces new genetic information into our population. This is important as it allows us to explore different types of solution which may perform better on our problem. Here you can see we've selected solution E at random, selected its head gene at random, and added some random number which has made its head wider. The 6 solutions you now see will be taken to the next generation, as we loop back round to the evaluation stage. And here you can see with this simple example that the population for generation 2 already looks better than the population for generation 1. As we saw on the hurdle problem, the solutions with longer legs seemed to perform better. Now imagine that instead of stick figures we had solutions which described the structure of a bridge, and the problem would be simulating vehicles crossing that bridge. I hope this simple demonstration has helped you understand the evolutionary algorithm process. So, if you're interested, what can you check out next? You can check out this link, which I will also put in the description. Here, evolutionary computation is used to design a vehicle and test it within a physics engine. It can be fun to watch and also allows you to tinker with some of the settings, which can be interesting. If you're interested in reading something a bit more in depth, I recommend this book and these academic journals. If you're interested in my publications, please visit my website where you can find up-to-date links and information. Depending on the feedback I receive and when in time you're viewing this video, you may see an annotation here linking you to a follow-up video where I cover more areas of evolutionary computation. And we've made it to the end. I hope you'll be leaving this video with some understanding of why evolutionary computation is exciting, what it is, how it works, and some ideas of where to go next. Thank you for watching. Some of my contact information is on screen and also in the description. I look forward to hearing your feedback and any requests for future videos. Thanks again.